So I'm just going to breeze through most of the material. If I were you, I wouldn't make an effort to try to copy the notes. No, after all, I supply you those slides later on. No? Just take note of the things that I say maybe that may be important. Okay, where did we leave off last time? So last time, I went with you through the procedure for determining the hybrid pi parameters, the unilateral hybrid pi parameters of transistor amplifier circuits. Right? So given a generic circuit, how do you get GM? How do you get RI? How do you get RO? And how do you get A sub V? Although if you know GM and RO, you already can get A sub V, no? Because A sub V is minus GM times RO. So we went through that procedure. So it's just a matter of knowing the definition of the hybrid pi parameter and then establishing the correct input or output conditions, right? Whether it's zero input or no load. Okay? Applying the test voltage where you should apply the test voltage, and then computing for the ratio that you want to compute for. Actually, if you know that, that's practically the entire module, basically. So I don't know if you had an opportunity to practice on what I told you to do. Kasi what did I tell you to do last time? We discussed, the last time we met, we discussed the transistor amplifier, two transistor amplifier configurations. One is the traditional common emitter amplifier, and then the second is yung collector to base biased transistor amplifier. And you went through the process of solving for the hybrid pi parameters. Okay, the next topic we were supposed to discuss is the common emitter or common source amplifier with the generation resistor. And that the generation resistor is for the common emitter, it is this RE. And I said, okay, this is a typical circuit. Yeah, this is a typical circuit. This is a fixed bias circuit, no, with the generation resistor. Actually, pag linagyan natin ng generation resistor, hindi na talaga fix yung bias. Nagbabago na yung bias. Okay, so I told you, okay, this is the equivalent circuit. Practice. I don't know kung nag-practice kayo. Try solving for GM, RPi, and RI, and RO. Hopefully you did. Okay. Anyway, the process for solving GM is IO over VI at no load. VI is a test voltage. IO is the current that will flow when your output is shorted. That's why you call it no load. And to do this, first you get the KCL at C. You get KCL at C. Sorry. Dito, you get KCL here. And you come up with this equation. Ano? And you can see that, no? IO, pag titingnan nyo, IO, this current, is VO over RE, VO minus VE over RO, okay? And then plus GM VBE. So yun yung tatlong term dito, no? VO over RE, VO minus VE over, this is wrong, this should be RO, no? Sorry about this. VO minus VE over RO. Okay. Plus GM VBE. Okay. But we know that VO equal to 0, VBE is equal to VI minus VE. VBE, itong VBE, is just VI minus VE. So finally, you get IO is GMVI. This should be 1 over, not RE, no? This should be 1 over RO. 1 over RO plus GM. So that's the first equation that you form. Then the second equation, you do a KCL at E. KCL at this point. Okay. So what is your KCL? That is VE minus VI over R pi. So yun yung first term. VO over RE at E, ano? Yung current na nagagaling dito, Teka, let me. Sandali, ano? This should be minus VE over RE. Sorry about the mistakes. This is VO minus VE. No. Sorry. Tama. VO over RC. This is RC. Ba't ko ulitin natin, ano? Sorry about this. Let me just erase this, ano? Okay, una yung KCL at KCLD. First of all, okay, we're computing for GM. So GM is equal to IO over VI. This is at no load. Okay. So what is no load? No load is you short this. Okay. This is now your I's of O. And then you apply a test voltage here. So this is VI. So the first thing is we do a KCL here. KCL at C. No? So what is your KCL there? That is your current flowing through RC. Your current flowing through RC, that is VO over VO over RC, okay, plus VO minus VE over RO. So yun yung current dito, VO minus VE over RO, okay, plus okay, ito, plus GM VBE. This is equal to 0. Okay? This is equal to I's of O. This is equal to I's of O. Again, no? I's of O, that's VO over RC, VO minus VE over RO, plus GM VBE, that is equal to I's of O. No? Now you recognize that VO is equal to 0. That's equal to 0. And then itong VBE is just VI minus VE. So finally, I get V sub O over RC minus VE over RO, okay, plus GM VI minus VE is equal to IO. Yun yung first equation. So this is one equation. No? And then the second equation is dito sa node na to. No? So KCL at E. Okay, what is that? That is VE minus VI over R pi. So yun yung current na nagpo-flow dito, palabas, plus VE over RE, no? That's the current down here, okay, minus GM, but VBE is VI minus VE, no? Yun yung value ng VBE. Okay, so that is the current flowing here, no? So how many currents? There are four, current flowing here, no? Pababa. And then the current here is VE minus VO over R sub O. This is equal to 0. But this is equal to 0. So from this, I can express V's of E in terms of V's of I, no? V's of E as a function of V's of I. Okay? And then I can substitute that here, no? I can substitute that dito sa values ng VE dito, VE rito. And what I'm going to come out with is a single expression expressing I's of O in terms of V's of I. Kapag ito, sinubstitute ko rito. No? I'm going to get an expression for I's of O in terms of V's of I. No? I don't trust this anymore, no? Because I saw some mistakes. I was just doing this before coming here. Okay, anyway, that's how you get GM. That's how you get GM. Okay, so dapat magagawa din niyo yung procedure for getting R's of I, and then magagawa din niyo yung procedure for getting R's of O. Okay, I want to do something a little bit different. Ang gusto kong gawin, I want to characterize this structure by itself. In other words, ito, I want to characterize this by itself, come up with, no, well, this is the circuit for this. And then once I characterize this by itself, in other words, getting the GM, RI, and IO for this particular circuit, that is when I will insert it back here. No? So that's when I will add RB and RC. So ito lang muna, no? Ito lang muna yung kukunin ko. I characterize this. Then after that, I add back RB and RC. Okay? So how do I get GM? GM is I's of O over V's of I. So let's do the same thing, no? I's of O over V's of I. No? So what do? I short the output. I apply a test voltage at the input. If I do a KCL at C, okay, so that's V's of O minus VE over R's of O, yun yung first term. No? Plus GM, VI minus VE. So that's two components of current. No? Remember, this is I's of O. Okay, that's I's of O. So that's this current plus this current. So this current is the first term. This current is the second term. Now, recognizing that V's of O is equal to 0, ito yun, V's of O is equal to 0, and simplifying, I get this expression. Okay, then I do a KCL at E. KCL at E, how many terms do I have? So KCL ko sa E. I have 4 terms. You have a current here, no? You have a current here, you have a current here, and you have a current here. So those are 4 terms. So the first term, VE minus V's of I over R pi. So yun yung unang term. And then I have VE over RE. That's the second term. VE minus V's of O over R's of O. So that's the current flowing through R's of O. And then finally, minus GM, VBE. But VBE is VI minus V's of E. No? And then I impose that the output is 0 because we are doing this at no load. So again, I have 2 equations. I just combine the 2. From this equation, I can get an expression for V's of E in terms of V's of I. And then I just substitute that here. And I'm going to get an expression for I's of O in terms of V's of I. And then I can get the ratio. So I combine the 2 equations and solve for I's of O in terms of V's of I. And this is what I'm going to come out with. Okay. Now, you look at it, you say, nakakatakot naman tignan yan, ano? Do I have to memorize that formula? Actually, pag may mga figures na yan, when you're given a circuit, you know the value of GM, RE, R pi, RO, RE, hindi naman ganyan yung magiging solution, ano? Gagamitin na niyo yung mga calculator ninyo para ma-solve niyo yung G's of M. So it's not that scary when there are already figures, when there are already quantities for R pi, RO, GM, RE. Okay, now what I want to do is, let's consider typical values. Okay. If you take a look at R pi, R pi is usually in the kilo ohm range. Do you remember the formula for R pi? R pi is beta over GM. GM is ICQ over V sub T. Ang ICQ natin usually nasa milliampere range yan. For typical transistors, that's in the milliampere range. For integrated circuit transistors, syempre maliit na maliit yun, that would even be in the microampere range. But let's say it's a typical transistor milliampere range. V sub T is 26 millivolts. Okay, so what you're going to get is GM in the let's say 10 millisiemens range, no? In the tens of millisiemens. Let's say 1 MA over 0.026. No? That will give you actually mga 20 or 30 millisiemens. I don't exactly know, no? So GM will be in the 10 in that range, no? Now R pi is beta over GM. Beta alam natin, ano yung ginagamit yung beta usually, no? 100 ang unang pumapasok sa ulo nyo kasi yun lagi yung sa example. So 100 divided by, let's say, something in the millisiemens range, you're going to get something several K. Maybe up to 10K, a little bit higher than that, ano? So yung R pi is in the kilo ohm range. Okay? Yung RO is VA over ICQ. That will give you something maybe in the 50K range. VA, typical value for your early voltage is about 50 volts, sabihin natin. Okay. You divide it by milliamperes. So you're going to get something in the, let's say 1 MA, you're going to get something in the 50K range. And RE, for reasons that you're going to see later, usually we don't employ a value of RE that is greater than 1K. No. Yung RO natin is going to be very much greater than R sub E. Therefore, 1 over RO will be very much smaller than 1 over RE. If RO is very much greater than R sub E, 1 over RO will be very much smaller than 1 over RE. No? So if you take a look, ito yung 1 over RO, that will be very much smaller than this, 1 over RE. We can actually neglect this. Kasi mas malaki to, much bigger ito than this, so we can neglect that. Okay. Now R pi times RO, so I said R pi is in the kilo ohm range, RO is in the 50K range. If you multiply R pi and RO, sigurado that will be very, very much greater than 1. Therefore, if you take a look at 1 over R pi RO, that will be approximately equal to 0. So ito, na-neglect. I can also neglect that. I can also neglect that. Now, beta, remember, GM is beta over R pi. GM is beta over R pi. Therefore, beta is R pi times GM. And we know that beta is very much greater than 1. So if R pi GM is very much greater than 1, that means GM is very much greater than 1 over R pi. So if I take a look at this GM and compare it to 1 over R pi, this is going to be negligible. And therefore, I can also now neglect that. So these are for typical values of R pi GM and RO and RE. So if I simplify, ito na lang yung matitira. And if I further simplify this, no, multiply the denominator by the numerator and the denominator by R sub E, this is going to be my final value of GM. So for this configuration, my value of GM is reduced by a factor 1 plus RE GM. No? I have an original value of GM. I'm going to divide that by a number which is greater than 1. This is greater than 1. So you divide GM by a number greater than 1. Siyempre, liliit yung G's of M. So it is reduced by a factor 1 plus RE GM. And that is the effect of Rs of E. The effect of Rs of E is it reduces the transconductance. If it reduces the transconductance, what happens to the gain? Will it increase or will it decrease? What is your formula for gain? You're all looking at your notes, no? You don't want to look at me. Ano yung formula for gain? Minus GM times small r's of O. So if GM becomes smaller, then your gain becomes smaller. And that's why you call R's of E a degeneration resistor, because it degenerates the gain. It degenerates the gain. And take note, the larger the value of RE, the greater the gain is reduced. That's why I told you that typically we don't make RE greater than 1K. If ever sana, let's say mag-reduce yung gain, we don't want it to reduce by a very large factor, no? So we want to keep this RE times GM quite small. Okay. So if for example, no, if GM is 1 millisiemens, kunwari GM natin is 1 millisiemens, which is actually a small value of GM, ano? Then RE is 1K. So what happens, no? Our gain is reduced by a factor of 1/2. Nangakalahati. Because you now have GM is GM, capital GM becomes small GM divided by 2. Okay, what is the effect of R's of E now on R's of O? R's of O. So nakita na natin yung effect of R's of E on G's of M. What is the effect on R's of O? So how do I compute for R's of O? That's V's of O over I's of O under zero input conditions. So zero input conditions, I'm going to short my input. I'm going to apply a test voltage at V's of O, determine I's of O, and then get the ratio of V's of O over I's of O. So ganun din yung procedure, no? I'm not going to go through the procedure with you anymore. So you can get you can do a KCL here. No, there will be 3 terms. I's of O is equal to VO minus VE over R's of O plus GM I forgot to show that here. No, this is GM VBE, and then this is E. Okay. But what is VBE? What is VBE? VBE is, well, this is 0 minus VE. So VBE is actually equal to negative VE. Kasi ang voltage dito will be 0 dahil shorted yan dito sa ground, ano? So that's 0 minus VE, that is VBE. So yun yung ipapasok natin dito sa loob na to. Okay. Again, go through the process. That's an exercise for you. And then applying typical values of RE, RPi, RO, and GM. This is what is going to come out as my output resistance. It is going to be my original output resistance, pero madadagdagan siya. Ang madadagdag sa kanya is 1 plus RE times G's of M. And if I do the same thing for my input resistance, how do I get my input resistance? This time I apply a test voltage here, V's of I, and then I do a no load condition. So I short my output, and then I get V's of I over I's of I. If I compute for that, ang mangyayari, my input resistance now will be R pi times 1 plus RE G's of M. So notice that we see that term, these are for typical values, no? For typical values, we see the term 1 plus RE G's of M several times. No? you divide the original small g's of m by 1 plus re g's of m, and that will give you the new g's of m. And then you multiply your ri by 1 plus re g's of m, that will give you the new capital Ri. You multiply your ro by 1 plus re g's of m, that will give you the new r's of o. So parang ganito. This is now for the transistor with the degeneration resistor. So ito yung bagong Ri natin. We just multiply the original with this. Ito yung bagong G's of M natin. Forgot the V's of I here. No? Should be a V's of I here. Okay. Ito yung bagong G's of M natin. I divide by 1 plus Re G's of M. And then this is my new R's of O. I multiply it by 1 plus Re G's of M. Okay. This is for a BJT. Now, it's going to be the same for a MOSFET. Basically, ang kaibahan lang ng MOSFET, if we go back to the model of the MOSFET, what is the difference with the MOSFET? So MOSFET, this is open. R pi is equal to infinity. This is open. Okay? Otherwise, everything else is the same. So if I go back to these equations, no, and just consider R pi equal to infinity, I'm going to get the same results. Kasi kung infinity yung R pi, lalo nang this is going to be equal to 0. Kung infinity yung R pi, lalo nang ito magiging 0. Right? And then we already said that 1 over RO is very much smaller than 1 over RE. Kaya neglected to. And I'm going to come up with exactly the same. Exactly the same model. So you can see that the common emitter and the common source are actually very, very similar. Okay. So, going back to, going back to this circuit. So how do I analyze this circuit now? No? How do I analyze this circuit? Ngayon, dun sa bago kong model, I just add now RB and RC. Where RB is in the small signal model, RB is from the base to ground, no? Because in small signal, VCC is equivalent to ground. And RC is from your collector to ground. So basically, ito yung bago kong model. This is my new model. I just add now my RB here. And then I just add now my RC here. So now if I add RB and RC, I'm going to get, again, new parameters. So what is going to be my new R's of I? It's just going to be RB in parallel with R pi times 1 plus RE G's of M. Again, these are considering typical values of your transistor parameters. And what is going to be my new R's of O? It's going to be this in parallel with this. Okay. Now, why do we accept using typical values? Sa totoo lang, no? When you have a transistor, for example, you don't really know the exact values. There is always what a tolerance. No? Even from transistor to transistor, same part number, may tolerance yan. So sometimes it's not worth it to be exact because you don't know, no? Yung mga tolerances ng mga parameters mo, you don't really know what they are. So it's not really worth it to be very exact. This is in the real world, no? Ngayon, here in class, we teach you the exact formulas, okay? But in practice, no? Hardly ever do you use the exact formulas, no? Usually you just use the approximations because of the reason that I just mentioned, no? Okay. So kung sa problem sinabing okay, calculate the exact as an academic exercise, that will really be just an academic exercise because you don't really do that in real life, ano? Pag sinabing calculate the exact, no choice kayo, no? Gagamitin niyo tong expression na to. Hindi nyo tatanggalin yung mga terms that are negligible. And you should know how to get this expression because we already learned how to determine all of the hybrid pi parameters of a particular circuit. Okay, are there any questions before we leave this topic? Any questions? Okay. So let's go to the small signal analysis of other transistor amplifier topologies. So dalawa na yung pinag-aralan natin. Yung common emitter. Common emitter or common source, yun yung una. Then common emitter, common source with the generation resistor. Then I gave you an example of common source with drain to gate feedback, no? Just as an exercise, just so you could practice the process. So ngayon, tignan natin yung common gate, common base, at saka common drain, common collector. So let's first take a look at the common base, common gate. Whatever we compute for the common base, yun din yung lalabas for the common gate. Because like I said, the models are the same. Mas simple nga yung MOS eh. Kasi yung MOS, ito is infinite, no? So your computations often come out simpler. That's why I would prefer showing the computations for the BJT because the MOS can be derived from the BJT by just assuming that our pi is equal to infinity. Okay, so this is our typical common base amplifier. That is not how it looks in an actual circuit. How does a common base amplifier look in an actual circuit? If you take a look at the common base amplifier in an actual circuit, let me draw that. So usually we use a biasing scheme. The best biasing scheme that you know of would be the self-biasing scheme, no? The transistor divider, the resistor divider biasing scheme, no? So usually nakikita natin yan. You have R1, you have R2. Okay. And then you have your RE. And then you have your RC. And then this is VCC. These are both ground, no? Yun yung standard biasing scheme na alam natin na medyo maganda. May mga ibang biasing scheme, ano? Yung mga fixed bias, for example, or yung collector to base bias. But this is the basic biasing scheme, no? Okay, if it is common base, where do we put our input? We put our input at the emitter. So saan natin ilalagay yung input natin dito, no? So this is V capital I, no? Or let's just use IN, capital IN. And where do we get our output? We get our output dito sa collector. So V, this is V capital OUT. Okay, may kulang dito. May kulang, ano? To establish the gate, the base as your common for small signal, we actually have to put a capacitor here. Remember what we said about that capacitor for small signal or for your AC component? That's equivalent to a short circuit, no? purpose of biasing, that capacitor is an open circuit. So walang effect yun sa biasing. But for small signal, time varying component, that is equivalent to a short circuit. So that establishes the base as your common. Okay. Yes, no? So what happens here? Okay. If I draw now, my small signal equivalent, okay, so this is the basic small signal equivalent of the transistor. And then dito sa base, I have two resistors connected to ground, no, sa small signal, R1 at saka R2. Okay? Two resistors connected to ground. But the base is already connected to ground. So those two resistors are just shorted. No? Kasi magkakaroon ka ng R1 at saka R2 dito, no? There's going to be R1 in parallel with R2 connected to ground. But since your base is ground, this ends up being shorted. Okay? And then I have an emitter resistor here, no? Okay? So there will be this emitter resistor. So that would be the more realistic model, or the more realistic the more realistic model of this, ano. Magkakaroon ng emitter resistor dyan. Okay, but let's just consider this, no? Let's just consider the basic. The basic. Okay. So how do you compute for G sub m? How do you compute for G sub m? So G sub m is I out over V in at no load. So ganun din, no? This is no load, so we short this. Then we determine I sub out. We apply a test voltage here. Our input is at the emitter, right? Yung input natin nandito sa emitter. This is equivalent to a short. So in effect, I'm applying a test voltage from my emitter to ground. Again, no, kalimutan muna natin tong R sub E, no? Let's not put that there first, no? Okay. In other words, let's just assume that this is what we are considering. So if I compute for I sub out, that's V out over RL, in your first term. V out minus V in. No? The voltage here is V out. The voltage here is V in. No? Take note that in this particular case, VE is equal to V in. The voltage at your emitter is equivalent to V in. So V out minus V in divided by RO. So ito yun, yung second term. And then now you have GM, 0 minus V in. No? VBE is 0 minus V in. So yun yung third term. Okay. So finally, I get the ratio of I out to V in. No? V out is 0, no? So this cancels. This cancels dahil 0 nga yung output ko. Right? So those two cancel. So I can get the ratio of I out to V in. Ito lang yung lalabas. This. Minus GM minus 1 over R sub O. So this is the exact. This is the exact expression for capital GM. Minus GM minus 1 over R sub O. Now remember what I said, R sub O is very large. And therefore 1 over R sub O would be approximately equal to 0. And therefore, we can approximate GM to be just equal to negative GM. Negative GM. Remember what we said about the common base? The gain is positive. Gain is positive. Gain is minus GM times R's of O. So kung GM natin negative, minus a negative value is positive, kaya nagiging positive yung gain natin, no? For a common base. Okay, how do you get R's of O? R's of O, again, no, just considering this basic circuit, is V out over I out at zero input. Ano yung zero input? Yung input natin is shorted to ground. So this is our zero input. Okay, that's our zero input. That is V in is equal to 0. Okay. If this is 0 and this is 0, what is VBE? What is VBE? 0, right? Kasi yung voltage dito sa base is 0, yung voltage dito sa emitter is 0, di syempre yung VBE natin will be equal to 0. Therefore, what is GM-VBE? That is just 0. In other words, this is an open circuit. If this is an open circuit, if you take a look at the equivalent circuit, what do I have across V out? I just have this RL in parallel with this RO. Right? So yun yung R's of O ko. It is just small RO in parallel with itong resistor na to, which I called RL. L signify standing for load. No? I could have called it RC. I'm just being consistent with the notes. The notes calls it R's of L. So this is the value of R's of O. This is for your common base. Now what about R's of I? Okay, R's of I, V in over I in at no load. So ano uli yung no load? We short the output, no load. And then we apply a test voltage here. You're going to get a current flowing, I in. So I just get the ratio of V in over I in. So what do I have to do? I have to get an expression for I in. No? So to get an expression for I in, I apply KCL in this particular node. I apply KCL at E. So this is KCL at E. So what is I in? Okay. V in, that is the voltage here at E. The voltage at E is V in divided by R pi, because this is grounded. So that is the current flowing upward in R pi. Okay. Then you have a current flowing downward here. So it's negative minus GM. But VBE is 0 minus V in. So GM 0 minus V in. And then I have V in minus the voltage at this point divided by RO. But what is the voltage here? That is also grounded. So the voltage here is 0. So I just have V in over R's of O. So if I simplify that, that is I in is V in multiplied by 1 over R pi plus 1 over RO plus GM. If I get the ratio of V in over I in, which is Ri, getting the ratio of V in over I in, it's just going to be 1 over R pi plus 1 over RO plus GM. You can think of GM as a conductance. Tama? I mean, you call it transconductance, ano? You can think of it as like a conductance. So if you get the reciprocal of GM, that's actually a resistance value. And Ri ends up being just the parallel combination of R pi, Ro, and 1 over GM. Parallel combination of these three. Okay, you compare the three. R pi, Ro, 1 over GM. Ano yung pinakamalaki dun sa tatlo? R pi, Ro, 1 over GM. Anong pinakamalaki? Medyo sinabi ko na kanina, no? Yung pinakamalaki yung Ro. Ro, no? Ro would be in the tens of K. Tens of Ks, no? Kasi isipin nyo, VA over ICQ. Yung ICQ nga is in the MA. VA is about 50 volts above. So that would be, kung ang ICQ natin is 1 MA, that's 50K. 50K ohms. So pinakamalaki is Rs of O. Susunod is Rs of pi. No? And then the smallest will be 1 over GM. The smallest will be 1 over GM. So dun sa tatlo, yung pinakamaliit would be 1 over GM. Okay? Now when you have 3 resistors, or let's say n resistors in parallel, the equivalent resistance will always be smaller than the smallest of all of those resistances. Okay. And when one resistor is very much larger than when one resistor is very much larger than another resistor, if you put them in parallel, the equivalent parallel combination will most likely be very close to the small resistor value. So yun yung nangyayari rito. Since ito yung pinakamaliit, if I put these three in parallel, the parallel combination will just be approximately equal to 1 over GM. Okay, just a few notes that I wanted to point out. Bakit importante yung Rs of I? Importante yung Rs of I because Rs of I dictates the loading effect on the input. It dictates the loading effect on the input. So if this is my amplifier, this is my amp. So this is my output. No? So this is V out, VO. Okay. This is my input. Ang nakikita rito ng input is Rs of I. Yun yung nakikita ng input. So here you have Rs of I. Now if my source has a series resistance, let's call this Rs of S. If my source has a series resistance, and all sources have series resistances, no? Kung ideal yung source mo, if your source is ideal, then the series resistance is equal to 0. But there's no such thing as an ideal source. All sources have series resistance. You might think of this as the Thevenin equivalent looking into the source output. No? The Thevenin equivalent would be, okay, yung V of I would be your open circuit voltage, and then Rs would be your Thevenin resistance. So kung meron resistance, what voltage actually gets delivered to my amplifier? You have a voltage divider. Ang nade-deliver sa amplifier ko would be dictated by the voltage divider formed by Rs and Rs of I. How do I get most of this delivered to the amplifier. Most of that voltage delivered to the amplifier. Sana, yung Rs of I is as large as possible. As a matter of fact, if Rs of I is equal to infinity, then I don't have any voltage drop across Rs of S, and all of my V's of I would now end up being delivered to the amplifier. Yun ang gusto kong mangyari. So importante yung Rs of I. The larger the value of Rs of I, the more of the input voltage that would be delivered to your amplifier. Okay? Unless, of course, ideal yung source natin na zero yung value ng Rs of S. Okay, pag tinignan natin yung common emitter na walang degeneration resistor, yung simpleng common emitter lang, ang Rs of I natin would be Rs of pi. Okay? And we know that that is relatively large. That is relatively large. So, re-reduce yung loading effect. If we take a look at the common base, my Rs of I is these three in parallel, which is approximately equal to 1 over G's of M. And that can be small. No? That might be small. At least not in the tens of case, for example, no, or single digit case. That might be small. Meaning to say, my common base will have a larger loading effect. So that is the disadvantage of the common base. The common base is nice because it has a positive gain, but from the point of view of loading effect, the common base is not as good as the common emitter. Okay, is that clear? No. Now, sometimes we want to control the value of Rs of I. There are times when you want to control the value of Rs of I. When does that happen? No, when you, instead of transmitting the largest possible voltage, what you want to transmit is the maximum possible power. There's a difference, no? If you want to transmit the largest possible voltage, you want Rs of I to be as large as possible. But if you want to transmit the maximum possible power, what should Rs of I be? From triple E 1 to 3. Kung gusto kong maximum power yung pupunta dito, what should be the value of Rs of I? Nakalimutan na ninyo? You don't remember? Should be Rs of S. No? Maximum power transfer. I guess you forgot that already, ano? Okay, so may role din yung common base. When you want to control the value of Rs of I for maximum power transfer, sometimes you might have to use the common base amplifier. Okay, I'm showing here the results for common gate. No? So you get similar results for the common gate. Parehong-pareho. No? Okay, the difference is maybe here. Kasi nawala itong R pi. R pi is equal to infinity. Kaya tatanggalin mo na. So imbis na R pi in parallel with RO in parallel with 1 over GM, it's just RO in parallel with 1 over GM. Any questions? So that is your common base or common gate. So this is the last, common collector or common drain. So again, this is the basic circuit for your common collector. If I draw the small signal equivalent of this entire circuit, so you start again with the transistor. So this is the transistor. Okay. Your input is applied to your base to ground. So that's shown here. My input is applied from base to ground. Small signal, my collector is shorted to ground. Because VCC, small signal, is equivalent to a short to ground. So my collector is shorted to ground. Where do I get my output? I get my output at the emitter. So this is my output at the emitter. And I have from my emitter to ground, I have my load resistor. No? And then take note, VE is equal to V out. My output now is equal to VE. Dun sa common base, my output is equal, my VE is equal to VIN, no? Sa common base. Dito sa common collector, VE is equal to V out. So again, GM. Okay, magsawa na kayo dito, no, sa process na to. That's I out over V in at no load. So what do? No load means I short my load. I compute for I of out. Okay, so let's take a look at the terms. How many terms are there? I of out. I have a current here. I have a current down here. I have a current going down here, and I have a current flowing up there. 4 terms that make up I of out. No? So nakikita niyo, no? V out over R of O, yun yung una. Right? Remember, this is grounded. So you have V out over R of O. No? Then you have V out over R of L. Ito pala yung una, no? V out over R of L. Ito yung V out over R of O. Okay, you have V out minus V in over R pi. And then minus GM, VBE, but VBE is V in minus V out. No? If you take a look, VBE is V in minus V out. And then recognizing that V out is equal to 0, so this disappears, this disappears, this disappears. Anong natitira? Ang matitira, I out is just negative V in 1 over R pi plus GM. Yun ang matitira. So if I get now the ratio of I out to V in, which is capital G's of M, that's just 1 over R pi plus small gm, which is, again, approximately equal to negative gm. Okay. R in. R in is V in over I in at no load. No load is short. Okay. So shorted na rin tong R of L, right? This is now shorted. So if I get V in over I in, ang matitira, ito na lang. Itong resistor na lang, R pi. That's why R of I is just equal to R pi. This is the common collector. And finally, R of O, What is R sub O? V out, I apply a test voltage here over I out at zero input. So ang gagawin ko, mag-KCL ako rito sa node na to. Apat na terms yan, 1, 2, 3, 4, that make up I sub out. So that's V out over R sub O, yung una. V out over R sub L, pangalawa. V out over R sub pi. No? Kasi pag tinignan nyo, this is also connected to ground. No? So the voltage here, V out over R sub pi. In fact, if you take a look at this, and this are really all in parallel. Okay? Finally, minus GM, 0, kasi yung VB is equal to 0, minus V out. No? VE is equal to V out. And if you simplify, yung R sub O natin will just be small r sub O in parallel with R pi in parallel with RL in parallel with 1 over GM. Ngayon, hindi ko alam kung ano yung value ng RL. Alam ko, between RO, R pi, and 1 over GM, pinakamaliit is 1 over GM. So I can already neglect RO and R pi. But since I don't know what RL is, no, my RO will approximately equal to RL in parallel with 1 over GM. So if you do product over the sum, product over sum, ito yung lalabas niyan. Okay. Any questions? So here I compare the different topologies. Okay. Unfortunately, I just picked up this table, no, from the slides. Wala yung common emitter, common source with degeneration resistor. Sana nandito rin, no? Maybe next time I'll make a complete table, no? But just comparing the three. So for your common emitter or common source, GM is just your transistor GM, small GM. But for the common base, common gate, and common collector, common drain, your GM is negative GM. So all of the three comparable, no, except that negative yung sa common base at saka common collector. If you take a look at the output resistance, R sub O, capital R sub O, in the common emitter and common base, that's just small r sub O in parallel with capital R sub L. R sub L is the load resistance. Whatever the load resistance, wherever the load resistance is connected. Sometimes it's connected to the collector, sometimes it's connected to the emitter, no? Or the drain and source respectively. And then for the common collector, common drain, this is what we just derived. It's RL in parallel with 1 over GM. So dito sa dalawa, it's RL in parallel with R sub O. Dito it's RL in parallel with 1 over GM. Sana ganun na lang linagay imbis na ganito, no? Para mas madaling tandaan. And then for your input resistance, so we know this is R pi. Okay, this is also R pi. Dito it's 1 over GM. So common base, common gate. So remember I said that this is smaller than this, and so it provides a larger loading effect. It loads the input source more kasi mas maliit siya. Less of the voltage coming from the input will get, less of the voltage coming from the source will get to the input of the amplifier if your source has a source resistance. Dahil maliit yung value nito. And then this is just a product of negative GM multiplied by R sub O. Actually, you only really have to know this tree because this one you can derive from minus GM times R sub O. Okay, so here, negative voltage gain. Here, you have a positive voltage gain. Okay, what is nice about this form? No, wala. Yun pa, no? Okay, if GM R sub L is very much greater than 1, what does this approach? No? Pag titignan nyo to, no? Itong common collector, common drain. Let's say GM times R sub L is very much greater than 1, then this approaches 1. And that's why this configuration, we sometimes call it a buffer, because the gain is something close to 1. Okay. The gain is something close to 1. Okay, so I guess that's it, no? That's what I prepared for today. That there are some odds and ends that are discussed in the notes. Na pag-aralan na lang yun ng sarili nyo. No, if you have any questions, you can always post it, no? Post it in our forum or even email me directly. No? Okay. So the next topic, which is the start of the last 2 weeks of this course, is frequency analysis, where we will now consider the effects of the capacitors, the capacitances in the circuit on the response of your amplifier. The capacitors will come into effect mostly at high frequencies, because that's where the small capacitances have significant will have significant reactances or impedances. And in the last section, you're going to be working a little bit in the S domain. So that's the reason why sinabay dito sa course na to yung 133, no, so that you have some understanding of the S domain. Okay. Any questions? Well, I'll stick around here, no? There's still some time before my next class, so if you have any questions, you can consult me directly. Okay, thank you.